Alright, 7.5 video notes. This is the last section of chapter 7. We're kind of combining. We used to run two sections, but we're going to combine these two into one because I don't think there's quite enough material in both to take up 2 different days. So perimeters, areas, and dilations. So our learning targets for today, the things you should be able to do when we're all said and done, are find the perimeter and the area involving similar figures. So you don't always have to have all the dimensions. If you know the perimeter area of 1 and the scale factor, you can see how that affects perimeter and how that affects area. And there's some rules we need to follow. And then we need to look at similarity properties in the coordinate plane, namely dilations, where we are blowing something up or shrinking something down on the coordinate grid. Alright, so let's look at this first little section here. And it says example 3, but really it's example 1 because I've kind of shortened it from another set of notes. But it says use the right triangles below to find the scale factor, the perimeter, and the area for each. Alright, so first thing we need to do is we need to find the scale factor. So to find the scale factor, that's the magnification power, I have to see what do I multiply the smaller one by to get the larger one. So I find a side that matches. Maybe I use this hypotenuse. I have a 20 and I have a 5. So for scale factor, if I do the big divided by the small, that would be a scale factor of 4. So the scale factor is 4. Now let's go ahead and let's find the perimeter and the area for both, and let's kind of see what happens. So for this big shape here, when I do the perimeter and I add up all the sides, that would be 12 plus 16 plus 20 for a grand total of 48. So there's the perimeter. And when I do the perimeter of the small one, that is 3 plus 4 plus 5, which is 12. And this is kind of exactly what I think should happen. When I notice the perimeter on the small one compared to the big one, it is 4 times bigger. So whatever the scale factor is, you multiply that by the small perimeter to get the large one. So I'm going to kind of highlight this like this. Perimeter times scale factor, okay, should equal the big perimeter. So the little perimeter plus the scale factor should equal the big perimeter. It just follows it perfectly. Now area is going to be a little different story here. When I look at the area of the big triangle, it is 1/2 base times height. Well, the base is 16, the height is 12, so 1/2 of 16 times 12. Well, half of 16 is 8, and 8 times 12 is 96. Now let's look at the area for the small triangle. The area for the small triangle is 1/2 base times height, which is half of 12, which is only 6. So you're going to notice something different. Area does not follow the same pattern. You can't just multiply the area by the scale factor and get the new area. It's much larger than that. And to find out how many times larger it is, I'm going to divide the big area by the little area. And if I do 96 divided by 6, that comes out to be 16. So for this problem, the area is 16 times larger. You know, I would expect it to be 4, but it's 16 times larger. Now, there's a relationship between that number 4 and 16. And basically, here is what you need to get for the area. Okay? You take the small area. You're going to not multiply it by the scale factor, but you're going to multiply it by the scale factor squared. And that should give you the larger area. So there's that key little difference there. With area, you have to square the scale factor before you multiply it to get the new area. Perimeter follows exactly the same. Alright, let's look at a couple story problems off of that using that idea. So for number 4, it says find the area of DEF, which is a larger triangle, if the area of ABC is 9. So notice, I don't have the dimensions for the base and the height for this one, but I do know that the little area is 9. Now, I should be able to, if I do the little area times the scale factor squared, that should give me the large area. Alright, well, I need scale factor. I know what the little area is. The little area is 9 times, well, let's find the scale factor. The scale factor is the big divided by the little. Alright, so that scale factor is 4, same as in the example above. So I'm going to do 9 times 4 squared, and that should give me the large area. So that's 9 times 16, which is 90 plus 54, that's 144. So I can find the large area with and use the small area without knowing any of the bases of the heights, just because I understand this relationship right here. So you don't need individual dimensions. As long as you know one of the two areas in the scale factor, you're good too. Alright, so example 5, a small hexagon is similar to a larger hexagon scaled up by a factor of 3. Let's just kind of sketch that. So I have a small hexagon. Hexagon means 6 sides, which has an area of, actually I don't know the area yet. I just know I have a small hexagon. And then I know I have a larger hexagon that all the dimensions got multiplied by 3. Alright, so part A. So scale factor is 3. Everything is 3 times larger. So if a small hexagon has a perimeter of 18, what is the perimeter of the larger pentagon? I don't know why I wrote pentagon. That should say hexagon right there. So perimeter, I do the perimeter times the scale factor, and that should give me the large perimeter. So 18 times 3 would be 54 is the answer to this question. So if the perimeter was 18, the big perimeter should follow the scale factor. It should just be 3 times larger. Now the next one deals with area. It says the small one has an area of 12. So if the small one has an area of 12, alright, I should then be able to find the large area. So let's do this one. Little area times scale factor squared should be big area. So if the little area is 12, the scale factor is 3 squared. So that's really like 12 times 9. So the answer to this question is the area is 108. So that is the big idea from this section, is that perimeter follows the scale factor. It magnifies the exact same amount. The area, you need to magnify it by the scale factor squared. That's key. That's a critical component. Alright, moving on into dilations. These aren't too bad. These are pretty straightforward. So answer the following questions to the best of your ability. Same scaling. So in math, the word dilate means to, and I'm going to write these in here, means to enlarge or shrink a figure. So a dilation just blows it up or blows it down. If a scale factor is less than 1, your figure gets smaller. Alright? Like anything, if you multiply a number by another number and it's less than 1, it makes it smaller. If you multiply it by 1, it doesn't change. If you multiply by a number greater than 1, your figure gets larger. So graph the dilated image of triangle JKL using a scale factor of 2 and 0, 0 as the center of dilation. We're pretty much always going to use 0, 0 as the center of dilation for these problems. So let's put some coordinates down. Right now J is at 2, 4. Alright, so I went over 2, up 4. So J's at 2, 4. K is at 1, 1. And L is at 4, 0. Be careful you don't mix up the X and Y coordinate. Remember, X always comes first, Y always comes second. Now, this right here, this first one, this is called the pre-image or the before image. And now we're going to do a transformation. A transformation is basically, there are different types, and let me just kind of highlight this really fast over here on the side. For transformations, there are reflections. That's where you flip an object over a line. There are rotations, where you rotate it in a circle around a certain point. Earlier in the year, we did some translation stuff, where a translation is a slide, and then today's is a dilation. All right, so 4 different ways I can manipulate figures here. So now, after it undergoes this scale factor, this magnification, the new one is called the image. And remember from earlier in the book, we put this little kind of quotation mark up there, and that would be read as J prime. So we use the word prime when we want to talk about that. That's called J prime. So it's kind of like we have the old J and then we have the new J. So what I do with the scale factor is I simply multiply everybody by 2, all the pieces. So 2, 4 becomes 4, 8. 1, 1 becomes 2, 2. Well, 4 times 2 is 8. 0 times 2 is still 0. So now I have 3 new points. So let's get the points on the grid. We have 2, 2. We have 8, 0. And we have over 4, up 1, 2, 3, 4, 5, 6, 7. So here is my new triangle under a dilation or a scale factor of 2. I blew it up by a factor of 2. Okay, so this is the new J, that's J prime. This is the new L, L prime. And right here is the new K, K prime. Now, some things that I want you to realize here. Some things you should know is that if you notice, the sides should be parallel. So for instance, this bottom should be parallel to the other bottom. All right, this side should be parallel to this side, and the small one here should match up with the small one over there. So those sides should all be parallel to each other. And there also should be exactly half the length because it was a scale factor of 2. So some other little notes kind of to put over here. All sides are parallel, okay, with the image to the pre-image, and the sides are 1/2 of the whatever the image is. The pre-image is half the regular image. So if I were to use the distance formula and calculate some distances, I would see that they were exactly twice as big. All right, let's check out number 5. Key idea here I want you to take away is you multiply the coordinates by the scale factor to get the new shape. We're not going to get too in detail right now. That'll come later in the book. So this problem, same thing. The scale factor changes of 3. Let's get our points down. Point M is at 1, 3. Point N is at 3, 2. Point O is at 2, -2. And point P is at -1, 0. So now remember, we undergo a scale factor change. Sometimes they call the scale factor K. That's kind of a common letter that they use for scale factor. Okay, K. And so basically I'm going to multiply every single number up there by 3. So that will give me 3, 9. That'll give me 9, 6. Multiply 2 by 3, I get 6. Multiply -2 by 3, I get -6. -1 times 3 is -3, and 0 times anything is 0. So let's go in and put these on there. 3, 9, 2, 4, 6, 8. There's 3, 9, so that is the new M. 9 over 9 up 6. That is the new n, or n prime. O is at 6, -6. 2, 4, 6. So there is O prime. And then -3, 0 is the new P, P prime. And then I go ahead and connect these. If I were using a straight edge, it would be perfect, but I'm going to kind of sketch it the best I can. So, looking at this figure, it should be true that, like this line and this line should be parallel to each other. This one and this one should be parallel. That line should be parallel to that line. I'm not going to put 3 arrows and 4 arrows, but, the top should be parallel with the top, and this bottom should be parallel with this bottom. And the length of all the sides should be exactly, the big shape should be 3 times bigger than the bottom shape. Alright, that's about all I need for you to know right now about dilations in the coordinate plane. I believe there's only one question on the test, maybe 2, involving this, and if you can do what you did on this little worksheet, these 2 examples, you should be in really good shape. So I look forward to seeing you tomorrow, and we will get after the practice. See ya!